Our first shape for this unit will be the parallelogram. As you can see from the name, shapes of this kind will relate to our parallel vocabulary word we've seen in the past. Remember, lines that are parallel are coplanar, never intersect, and are always the same distance apart from each other at every point along their path. So, what does this mean for parallelograms? Parallelograms can look something like this. The shape itself obviously has 4 sides, which makes it a quadrilateral. However, each side is parallel with its opposite side, hence the name parallelogram. This is the main property that is required of a quadrilateral to be a parallelogram, which leads us to 4 main theorems. Firstly, given that the shape is a parallelogram, the opposite angles are congruent. Secondly, the angles that are consecutive to one another are all supplementary. This leads us to our third theorem. If a parallelogram happens to have at least one angle of 90 degrees, then according to the first 2 theorems, all adjacent angles must also measure 90 degrees, and all opposite angles must measure 90 degrees as well. This shape looks like one we've already looked at before, the rectangle. A rectangle is a parallelogram as well. Rectangles can also help us understand the last major property of a parallelogram. As we already know from rectangles, the sides opposite each other are congruent, and it's the same for all parallelograms, including those that are not rectangles. Fun fact, squares also satisfy the properties we've just discussed. They are parallelograms too. In summary, parallelograms have congruent opposite angles, supplementary adjacent angles, and congruent opposite sides. If this is parallelogram ABCD, we use this symbol to refer to the shape in writing. Like other polygons with 4 or more sides, parallelograms have 2 diagonals that can be drawn from opposite angles. These diagonals are special in 2 ways and come with 2 more theorems. Firstly, drawing one diagonal will split the parallelogram into 2 congruent triangles. This is true no matter which diagonal you choose to draw. Secondly, if both diagonals are drawn, they would bisect each other at a particular point inside the parallelogram. However, unless the parallelogram is a rectangle, the 2 diagonals that you can draw will not be congruent. This can be most easily seen with this elongated parallelogram. See how the 2 diagonals are clearly not congruent? It's the same case with more stubby parallelograms. Only the rectangle has congruent diagonals. Now we will examine 4 more theorems that are dead giveaways to conclude whether a quadrilateral is a parallelogram. These are called conditions. Only one of these conditions needs to be true for a quadrilateral to be considered a parallelogram. So condition number 1. If you find that at least one pair of opposite sides of a quadrilateral are congruent and parallel, the shape is a parallelogram. As you can see, if either side fails to be congruent, parallelism is lost and the shape cannot be a parallelogram. Condition number 2. If the 2 diagonals of a quadrilateral bisect one another, the shape is a parallelogram. At any time, if the diagonals are not both bisected, parallelism is lost. Condition number 3. If congruence exists with both pairs of opposite angles, then the quadrilateral is a parallelogram. If one pair fails to be congruent, parallelism is also lost. Let's test a few quadrilaterals and determine if they are parallelograms. Example number 1. Here we have a shape with each side having its own unique length. If we recall from condition number 1, at least one pair of opposite sides must be congruent and parallel. Even though we have one pair of opposite sides that are parallel, they are definitely not congruent, and therefore the shape is not a parallelogram. Let's look at example number 2. The shape we have here has a set of diagonals that bisect each other. We know this for sure because the image indicates that each diagonal is cut in 2 segments of equal length. This satisfies condition number 2 of bisecting diagonals, and therefore the shape is a parallelogram. Our last example looks kind of like a kite and has one pair of opposite congruent angles. Unfortunately, parallelograms require both pairs of opposite angles to be congruent. Since we only have one pair that is congruent, the shape is therefore not a parallelogram. For our last topic regarding parallelograms, we will study how to calculate the area of the parallelogram. While the shape may seem a bit odd to determine its area, you may notice that the parallelogram can be sliced here to create a triangle piece. This piece can be moved to the other side of the shape to form a rectangle. The area of a rectangle is easy to determine. We've seen it before. Length times width. The justification for calculating the area of a parallelogram like this is found in the area addition postulate, which states that a shape's area can be calculated by adding the individual areas of the shape's non-overlapping parts. The way we configured our parallelogram follows this same principle. The original shape looked like this before the split. Then, by following the area addition postulate, we added two non-overlapping regions to create an easier shape to determine its area. In our case, a rectangle. However, when talking about parallelograms, we call the length the base and the width the height. The official formula for the area of a parallelogram is A equals B times H, where the height, H, is the auxiliary line drawn perpendicular to the base, B. For example, if the base was 3 units long and the height was 1.5 units long, the area would be equal to 3 times 1.5, which equals 4.5 square units of area. Remember, parallelograms are unique quadrilaterals since both pairs of opposite sides are parallel. In the next video, we will discuss another unique quadrilateral, the rhombus, and discover what unique properties this new shape has.